Hello everybody, my name is eMoney Esedi. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 16. Please excuse my congested voice. I'm currently recovering from COVID, but I'm still doing good enough to start chapter 16. So that's what we're going to do. In this chapter, we're going to be discussing three big ideas. And these three topics are conjugation, molecular orbital theory, and pericyclic reactions. We're going to start off talking about conjugation. We're going to define this term, and from this definition, have a new class of molecules that we can talk about called dienes. Dienes are compounds that possess two carbon double bonds, and we're going to build a profile about conjugated dienes. Specifically, this profile will include important kinetic and thermodynamic properties of conjugated dienes. We're even going to look at addition reactions that are going to give us a practical / technical insight into how we can make dienes in a lab. Next, we're going to talk about molecular orbital theory. We're going to briefly touch bases on this. A little more than we did in chapter 1 of Organic Chemistry 1, if you remember. We're going to elaborate on this theory slightly more just so we can better understand conjugation. Warning, this topic can get very complicated, but we're not going to get into super complicated details of MO theory. You will do that if you take inorganic. Lastly, in the second part of chapter 16 videos, we're going to discuss pericyclic reactions, cycloaddition, electrocyclic, and sigmatropic, with a heavy focus on cycloaddition and sigmatropic specifically. All right, with that being said, now that you know the outline for this chapter, let's start with our first topic. What is conjugation? Conjugation exists when three or more atoms with the ability to resonate are adjacent to each other's. In other words, it is when three or more p orbitals are next to each other and can join together into this larger pi system, and we're going to elaborate on what this really means. But when we have a double bond, what forms and participates in this double bond are sp2 hybridized orbitals and a p orbital. Why is this so important? This is important because these p orbitals, they provide a highway for delocalized electrons to move around in a molecule. This overlap of p orbitals can extend to larger and larger p orbital systems. Now, the definition of a p orbital extends past just double bonds. In other words, the presence of double bonds isn't the only way to achieve this p orbital overlap. Other ways include having an empty p orbital, such as that in a carbocation, an orbital containing a lone pair, a p orbital of a pi bond, double or triple, and a half-filled orbital, such as that seen in radicals. So when we look at systems like this, for example, right, these double bonds are forming, part of these double bonds are forming because of sp2 hybridized orbitals and p orbitals, right? And when you have so many p orbitals right next to each other, all right, you get this idea of conjugation. All right, there's so many p orbitals right next to each other, and it provides electrons this sort of highway to move in. It allows electrons to delocalize within the molecule. All right. Now, the way that this can happen, again, we said it's not just your normal p orbitals from double bonds, but your p orbitals from carbocations, p orbitals that house lone pairs, half-filled orbitals, such as that seen in radicals. And if you notice very quickly, this is all the same criteria that we discussed when we talked about molecules that participate in resonance. Well, how exactly, you might say? Well, let's look at this example and work through it. All right? A molecule that has adjacent double bonds, like we drew in the previous page, all right, is called a conjugated diene. This right here, two double bonds right next to each other, right, is called a conjugated diene. In conjugated dienes, the pi bonds are separated by exactly one sigma bond. So look at these double bonds right here. Let's draw them out. Where's our pen? There we go. They're separated by 1 sigma bond. All right. Now, when double bonds are separated by more than 1 sigma bond, they are no longer conjugated. All right. They are referred to isolated dienes. Now, looking at these set of molecules right here, they might not appear conjugated at first glance because your assumption might be, well, we need double bonds within only 1 sigma bond apart from each other to form this conjugation, right? Because it's so easy to see with this kind of example. When you look at a conjugated diene, it is very easy to see why they might be conjugated. There are pi orbitals right next to each other to allow the movement of delocalized electrons. All right, but if you look at these set of molecules right here, it might not be so obvious that there are p orbitals right next to each other to allow for conjugation. All right, well, you'd be surprised that they, in fact, spoiler alert, are conjugated. And why is that? We're going to look at each example and see why. If we look at this first example, all right, it's conjugated because this positive charge, all right, this is a carbocation. All right, carbocations have empty p orbitals ready to be filled. All right, and we know double bonds already have p orbitals that participate in the double bond. And now look at that. You have a system of p orbitals right next to each other. This molecule is in fact conjugated. And now you know when you see a carbocation, all right, there is a empty p orbital there. All right, we could look at this second example. We see a negative charge, all right? This negative charge is from a lone pair that is housed in a p orbital. And so then if you draw all the p orbitals, look at that, they're right next to each other. You have conjugation within this molecule. All right. Now, again here, all right, you have this heteroatom, but this heteroatom also has lone pairs, and these lone pairs also reside within a p orbital. And again, this molecule is a conjugated system because of that. All right, and this last example, all right, you have just a single electron, all right, a radical. This single electron is also still housed within a p orbital. And so what you have, once again, is a conjugated system of p orbitals right next to each other. Bottom line is, if the atom between 2 pi bonds has a lone pair, an empty p orbital, or a radical, it can still participate in conjugation. All right? So that's really important to know. The but to this is if it's bound to 4 atoms like you see here, all right, it can't participate in conjugation. All right? There's no p orbitals for things to move within a complete conjugated pi system. So neither of these examples are actually conjugated. But remember, anything that is a carbocation, carboanion, there are lone pairs or radicals, all right, they can still participate in conjugation. All right, and that's really important to know. Now, with that being said, now that we understand fully what conjugation is, let's talk about dienes. All right, dienes are compounds that possess 2 carbon double bonds. All right, in cumulated dienes, the double bonds are right by each other. Like the pi bonds are adjacent, right? Pi bonds are adjacent. All right, in conjugated dienes, the pi bonds, these double bonds, are separated by exactly 1 sigma bond, right? This 1 sigma bond is what's separating the 2 pi bonds. In isolated dienes, the pi bonds are separated by 2 or more sigma bonds. All right, so our focus in this chapter is with conjugated dienes. All right, so let's build a profile for a conjugated diene. And the first thing we want to talk about in this profile for conjugated diene, what we need to know is how to prepare a diene? Well, a conjugated diene can be prepared from an allylic halide via an elimination process. So here you have, right, a allylic halide. Here's your double bond. This is the allylic position in reference to the double bond. And look at that. You have a halide, a halogen, in that allylic position, right? This is called an allylic halide. And starting with an allylic halide through an elimination process using, say, a bulky base like tert-butyl, what you can do is have an elimination process that will form a double bond there. And now what you have is a conjugated diene. All right, conjugated dienes can also be formed from dihalides. All right, so whenever you have two halogens next to each other, all right, conjugated dienes can be formed from this starting material through two successive elimination reactions. So two equivalents, say, of tert-butoxide can actually take this dihalide and convert it into a conjugated diene. All right, so that's something to keep in mind. Now, the second thing we want to talk about in the process of building a profile for these dienes is talking about bond length and bond length comparison. All right, so let's talk about the first consequence of conjugated dienes in regards to bond length. Well, the single bond in a conjugated diene, the single sigma bond, all right, that is separating the two pi bonds. We're gonna look at this one, right? This is a conjugated diene. This sigma bond, the single bond that's separating the two successive double bonds, all right? This single bond in a conjugated diene is shorter than a typical carbon-carbon single bond. The explanation for this actually stems from hybridization. The carbon single bond of a conjugated diene is formed from the overlap of two sp2 hybridized orbitals, while the carbon single bond in a normal molecule, say ethane, right, is formed from the overlap of two sp3 hybridized orbitals. Now, the more detailed explanation actually stems from molecular orbital theory, and we're going to get to that in a second. The last thing that we want to really talk about to finish off building this profile for conjugated dienes is stability. What we realize when we plot the energy or the enthalpy of an isolated double bond and a conjugated double bond is that the conjugated double bond are more stable. And again, the explanation for this stems from molecular orbital theory. Now, it's only fitting that we transition into talking about molecular orbital theory, since a lot of the properties of dienes comes from the overlap of its p orbitals, and this is best explained by MO theory. But let's first do just a quick practice problem or two before we segue into molecular orbital theory. All right, so let's do this practice problem. This practice problem says, identify reagents necessary to convert cyclohexane, all right, this is cyclohexane, into 1,3-cyclohexadiene. All right, so starting with just a normal cyclohexane, all right, we want to convert it into 1,3-cyclohexadiene. All right, notice that the starting material has no leaving groups. All right, so you cannot simply treat it with a strong base. That's a great hint right there. You must first introduce functionality into the starting material. All right, this is a great synthesis problem. All right, you did a couple of these in organic chemistry 1 near the end. All right, you're going to be seeing a ton more of these starting now. All right, so it's really good as you learn about different types of groups of molecules that you learn how to prepare them, because you're probably going to get a couple of synthesis questions within every chapter starting now. All right, and these kinds of problems are really going to require you to tap into your organic chemistry 1 knowledge, especially everything you covered from chapter 7 and onwards in organic chemistry 1. Now, I obviously will serve as a reminder here too whenever we're doing synthesis problems, but make sure that you do touch up on that material as well. All right. So they gave us a hint pretty much how to do this. All right. If you read this again, it says the first thing you need to do all right, is introduce a functional group, a good leaving group, a good functional leaving group. Actually, let's write that down. A good functional leaving group. And then you can do an elimination reaction using a strong base. All right, they kind of sketched out your step-by-step process for this synthesis problem. So now it's just up to us to recall what kind of reagents we need to introduce a functional leaving group and to do an elimination reaction. All right, so we're going to start off. We're going to draw our cyclohexane. All right, now what we can do to introduce a functional group that can be a good leaving group. Remember, good leaving groups, a really great example of this are our halogens. All right, what we can do to do that is do a radical bromination reaction to add, say, bromine. All right, we covered this reaction, I believe, in you should have covered it in chapter 12 of organic chemistry, if you followed the Dave and Klein textbook, of course. All right, and what you need is just Br2, all right, and some light, okay? And what this is going to do is it's going to add a bromine to your cyclohexane. Fantastic. All right, so now what we could do, we can form our first double bond using a strong base. All right, so say sodium ethoxide, we can do that. And what will happen now is we're going to form our first double bond. Fantastic. Actually, I want to draw the double bond here just because it's going to be easier. It doesn't matter. Makes no difference, all right? Now what we could do to this double bond, all right, this is going to require us to remember some of our addition reactions in chapter 8. What we can do now is to each side of this double bond, we can actually go ahead and add halogens to both sides of this double bond. We can do this through halogenation, all right? So just some good old Br2, and what happens is we can actually add bromine to both sides of this double bond. All right, of course, you're going to get the enantiomer of this as well. And now all you have to do is that elimination reaction with a strong base. This is pretty much taking a dihalide, all right, like we talked about when we talked about preparation, taking our dihalide, which is what we ended up with right here, and through two successive elimination reactions using a strong base, we can end up with our conjugated diene. All right, so we're going to treat it with two equivalents, right? Two runs of tert butoxide. And what's going to happen is we're going to have our two double bonds right here, our conjugated diene. In other words, our 1,3 cyclohexadiene. All right, fantastic. Let's do one more problem before we get to molecular orbital theory. All right, this problem says rank the 3 carbon bonds, carbon-carbon bonds of one butene in terms of bond length from shortest to longest. First step, let's draw this out. All right, one butene looks like this. All right, now let's number our carbons really quickly. 1, 2, 3, 4. Fantastic. All right, so what we want to do now is rank the 3 carbon-carbon bonds of one butene in terms of length, bond length. All right, so we have carbon 1 and carbon 2 forming a bond. We have carbon 2 and carbon 3 forming a bond. And we have carbon 3 and carbon 4 forming a bond. All right, now we know that single bonds are longer than double bonds. Double bonds are longer than triple bonds. All right, so our double bond here between carbon 1 and carbon 2 is going to be our shortest bond length, all right? Fantastic. Now all we have to do is compare C2 bonded to C3 and C3 bonded to C4. Well, the next shortest bond length is going to be C2 and C3, all right? And we discussed bond length when we were talking about our profile the single bond here that is directly bonded to a double bond is always gonna be a little bit shorter than a true single bond. All right, and it has to do with hybridization, and it also has to do the explanation with molecular orbital theory. So now we know that this is going to be the next shortest. So this is the first shortest. This is the second shortest. All right, and C3, C4 is going to be our longest bond, actually. All right, so hopefully that made sense. Now, since we did a few problems, now we can jump into molecular orbital theory. Now, if we want to talk about molecular orbital theory, I'm going to zoom out a little bit just so you can see this whole page. If we want to talk about molecular orbital theory, we're going to need to start from the beginning. Friendly reminder from some of the points we talked about in chapter 1 also. All right, so when we talk about electrons of an atom, all right, we use atomic orbitals to describe the probable regions that those electrons can reside in. All right, and that's where we get our s orbitals, our p orbitals, our d, f, and so on. All right, those orbitals represent probable regions that you can find the electrons of an atom. All right, this is for individual atoms. Now, what happens when two or more atoms form a bond? How do we describe electrons then? Well, when we started off Organic Chemistry 1, all right, we talked about how valence bond theory can be a potential theory that serves as an explanation, especially after we introduced hybridization. However, a more thorough, a better explanation for bonding can be described through molecular orbital theory. What happens with the electrons of two or more atoms when they form a bond? Well, MO theory does a good job of explaining this. Now, if we go back to conjugation and look at a pi system, a system of overlapping p orbitals, MO theory, molecular orbital theory, does a better job describing what all those p orbitals actually look like. All right, when you have a system of overlapping p orbitals, they're going to interact in a way, either constructively or destructively, to give off a whole new molecular shape. All right, and this is what we're going to soon learn and see as bonding and anti-bonding molecular orbitals. Now, how is this all done? Where does this explanation or this theory of MO originate from? Well, if you ever take quantum mechanics, you'll get a good explanation of this. It's done using what we'll call complicated math for now. All right, some linear algebra. It uses linear combination of atomic orbitals to represent molecular bonding orbitals that are associated with the whole molecule. So what are we going to do with this information? Well, we're going to learn how to draw MO diagrams for the pi systems in conjugated molecules. We're going to learn how to draw the MO diagrams for the overlapping p orbitals, all right, in conjugated systems. All right, let's restate though, because that's a lot of information. All right, when we have a single bond, all right, a carbon-carbon single bond, all right, a sigma bond. All right, a sigma bond, it's constructed from overlapping s orbitals. All right, so according to MO theory for sigma bonds, two s orbitals, right, one from each carbon, say, or one from each, or from hydrogen if we want to look at H2. All right, an s orbital from each hydrogen. All right, we're going to look at H2 instead. It's a more simple system for this. All right, we're going to take a sigma bond, right, is constructed from overlapping s orbitals. All right, MO theory says for sigma bonds, these two s orbitals are going to be replaced by two molecular orbitals, a bonding molecular orbital and a anti-bonding molecular orbital. The bonding molecular orbital comes from if the two s orbitals from hydrogen overlap and interact constructively. All right, and the anti-bonding molecular orbital comes if the two s orbitals from each hydrogen, they destructively interfere with each other. All right, so when we have a single bond from like H2, for example, all right, the two s orbitals from each hydrogen, they can either interact constructively or destructively, and so we get a bonding orbital, a bonding MO, and we get an anti-bonding MO. All right, now recall that a pi bond is constructed from overlapping p orbitals. So now, according to MO theory, these two atomic p orbitals can be combined to produce two new orbitals. All right, bonding MO and an anti-bonding MO. So for pi bonds, the two atomic p orbitals are replaced by two molecular orbitals, either a bonding MO or an anti-bonding MO. So let's look at this with several examples so we can draw the p orbitals, the p molecular orbitals for several conjugated dienes. Okay, so remember, whenever we looked at this example for a single bond, now with a double bond, all right, this double bond, for example, all right, this double bond is formed from two p orbitals right here. All right, these two p orbitals, just like the s orbitals we looked at before, can interfere constructively, all right, and form a bonding MO that looks like this, all right, or they can interfere destructively and form an anti-bonding MO like this. Now, with anti-bonding orbitals, MOs, right, you have nodes, you have regions where you're not gonna find your electrons, all right? Now, let's do MO theory for a conjugated diene. All right, so for molecular orbital theory for, say, butadiene, all right, the four atomic orbitals, the four atomic p orbitals are going to be mathematically combined to form or produce four molecular orbitals. All right, the lowest energy molecular orbital is going to have no vertical nodes. The next one is going to have one. All right, and each higher energy molecular orbital is going to have one additional vertical node. All right, these four molecular orbitals, all right, are going to be often represented with a shorthand drawing that we're going to learn. All right, and so to kind of put all this information that you're reading on these pages that I am telling you, we're going to do a quick example. All right, we're going to look at 1,3-butadiene right here. All right, we're going to look at the p orbital system. We're going to look at the overlapping p orbitals that make up this system. And then we're going to draw the four molecular orbitals, all right, that are going to come from mathematically combining the four p atomic p orbitals. All right, we're going to work through this step by step, so it's going to make sense, all right, how we can take the overlapping p orbitals of this molecule and draw the molecular orbitals for it. All right, so let's look at this molecule. All right, there's a p orbital here. There's a p orbital here. There's a p orbital here. And there's a p orbital here. There are four p orbitals. All right, fantastic. There are four p orbitals. Sorry, I zoomed out too much. Okay, so we're going to follow this step-by-step guide here. This step-by-step guide will help you draw the MO, the molecular orbitals, for any conjugated diene, all right? So, starting off with butadiene, the first step is the number of molecular orbitals you're going to have is going to equal the number of atomic p orbitals. All right, so we have four atomic p orbitals here. That means we're going to have four molecular orbitals, all right, that we're going to have to draw. All right, and that's 1, 2, 3, 4. Fantastic. All right. One orbital must never change phases, all right? And the first is preferred. And the last orbital must always change phases. Now, what that means is your p orbital, all right? Your p orbital looks like this, all right? One phase of the p orbital is usually noted as being positive and the other as negative. All right, so whenever you have a system like this where you're drawing 4 molecular orbitals, all right, 4 molecular orbitals for all the 4 atomic p orbitals, what you're going to have to do is start off by drawing all 4 of these for each MO, all right, and then you're going to have to figure out how to assign each p orbital individually here. So for your first molecular orbital, all right, there's no changing of phases. So all the top parts of each p orbital will be positive, all right, and all the bottom ones will be negative. There's no change in phase. Top is all the same phase, and the bottom is all the same phase, all right? Now, what this helps us illustrate is that one molecular orbital of 1,3-butadiene can have all the top parts of the p orbitals be in one phase and all the bottom ones be in a different phase. All right, now as you go up to your next molecular orbital, all right, the number of nodes, they began with 0, right? This has no nodes, right? Because all the top parts of our p orbitals are in the same phase and all the bottom parts of our p orbital are in the same phase. Now, as we go up in drawing the next p orbital, the number of nodes here has to increase. So we started off with nodes of 0. Now this molecular orbital 2 has to have a node of 1. On top of it has to have a node, 2 nodes. All right, and our last 4th molecular orbital has to have 3 nodes. All right, that means that somewhere in this drawing, all right, some phases have to switch up. All right, so if we have 1 node, all right, we're going to cut this in half. What that means, why we did that is this is going to be plus. Let me stick to the same color, sorry. Let's do blue. All right, the top phases for these 2 p orbitals are going to be plus, plus. All right, but then they're quickly going to switch up to minus, minus. There's a discontinuity right there. All right, this change between one positive phase and a different phase completely is going to form a node. And that's exactly what we need for MO number 2. We need 1 node. We need to introduce 1 node. And that's how we do it. We introduce one place where the phases switch up. All right. And it's the same way the top and the bottom. All right. There's going to be this one place right here. All right. Where the phases of the orbitals are changing. Okay. And they have to be symmetrical. So this is a good way of us making it symmetrical. Now, in this next MO that we want to draw, we need to have 2 nodes. That means we need 2 places that switch up phases. And we need to make this as symmetrical as possible. All right? This is part of the way we draw appropriate molecular orbitals. All right? So, if we want to have 2 nodes in this MO, all right, we need to make sure it's as symmetrical as possible. So what we could do is something like this, where we start off with a positive phase here, all right, and then we quickly switch it up to a different phase right next to it. All right, and we're going to keep that same phase, and then again near the end, once more, we're going to switch it up. All right, this introduces 2 places of discontinuity. All right, 2 places where our phases are switching up, hence the 2 nodes we need. All right, and then last but not least, the 4th molecular orbital that we're going to draw, the highest energy one, by the way, this is going in energy, all right, is going to have 3 nodes. All right, so we're going to have to draw 3 places where the phasors are switching up. All right, and so this is just going to go back and forth. So plus, and then this is going to be minus. All right, awesome. So we switched up the faces. That's our first node. All right, and then again, we'll switch it up. So that's our second node. And then once more, and that's our 3rd node. All right, and so that is how you draw the molecular orbital. All right, how you draw the molecular orbital of a conjugated diene. from the start, our conjugated diene has 4 atomic p orbitals that form this conjugated system. All right, that means we have to draw 4 MOs. All right, 4 molecular orbitals for this for 1,3-butadiene because it has 4 atomic orbitals. All right, starting from the bottom, you have to make sure, all right, that your molecular orbital number 1 has 0 nodes. That means there are no phases that are changing, all right, when you go through this, all right, from the top. All right, then your second molecular orbital, you're going to have 1 node, 1 place of discontinuity. All right, that means that at some point, all right, your phases are going to change. And the reason we did it halfway through here is because when you're drawing these nodes, you want it to be as symmetrical as possible. All right, awesome. Fantastic. All right, and then what we want to do is fill our molecular orbitals according to the rules. All right, so we have our 4 atomic p orbitals. We have these 4 electrons, and we've drawn all 4 of our molecular orbitals. All right, so now what we want to do is we want to fill these 4 electrons in the orbitals, all right, following all our rules. So what that means is 2 electrons to an orbital, all right, and you have to fill those both in before you go to a higher energy, and then there's 2 here, all right, and that's all 4 of our electrons. Our 4 electrons, okay, of a conjugated diene, right here, 1,3-butadiene, occupy the 2 lowest energy molecular orbitals. And that's really important to know. For any conjugated polyene, all right, the HOMO, the highest occupied molecular orbital, which is, by the way, molecular orbital 2, and the LUMO, the lowest unoccupied molecular orbital, which is MO3, are important MOs to consider and are called frontier orbitals. All right, so your HOMO is your highest occupied molecular orbital. What's our highest occupied molecular orbital here? Well, the electrons, the highest molecular orbital therein is the second MO, and the lowest unoccupied molecular orbital is MO3. All right, now you can also make a few more notes, right? The 4 pi electrons of a conjugated diene, the one that we looked at, 1,3-butadiene, all right, occupy the 2 lowest molecular orbitals, all right? These 2 lowest molecular orbitals, by the way, all right, are our bonding molecular orbitals. These 2 higher MOs are called our anti-bonding MOs. All right, the lowest molecular orbital, orbital 1 right here, exhibits double bond character between C2 and C3, while the second MO does not. All right, this exhibits double bond character. All right, our second bonding MO doesn't, though. All right, and it's a mix of these 2 facts that explains why the sigma bond between the 2 double bonds is actually shorter than a normal single bond. It's because of the blended characteristics of the 2 molecular orbitals that are occupied. All right, so that's how our molecular orbital theory comes into play for explaining why our sigma bond that is between 2 double bonds is shorter than a normal single bond. Now, we have here 1,3,5 hexatriene, all right? There are 1, 2, 3, 4, 5, 6 p orbitals here. That means there are 6 molecular orbitals that you have to draw. In order to draw all 6 molecular orbitals, you'll draw a straight line, and you'll draw all 6 of your p orbitals for each single one of these molecular orbitals, all right? That's always going to be your first step, all right? And then starting from the bottom at 1, this one will have 0 nodes, all right? Look how all the positive charges on the top, all right? All the same phases, all right? I know that positive and negative is here to help demonstrate that they're in different phases, all right? But everything is in the same phase here, all right? There's no place of discontinuity where something is changing phases. And that is what you want at your first MO, 0 nodes, all right? For the second one, you want 1 node, all right? For your third, you want 2. For your fourth, you want 3 nodes. For your fifth molecular orbital, you want 4 nodes. And for your last molecular orbital, for 135 hexatriene, you want 5 nodes. Now, before you start drawing, the phases of each of these p orbitals to demonstrate the appropriate nodes, you can simply draw where that discontinuity is going to happen, all right? So you have no nodes here, so you're not going to draw a place where the phases are going to begin to change, all right? But for MO2, all right, you're going to have 1 node, and so you're going to have 1 place where the phases are just going to change, all right? Remember, you want it to be symmetrical, so we can just draw it halfway here. So if you start off with all in phase, positive in phase on the first 3, then you're going to have to switch it up right here for the next one, right? So there's a area of discontinuity where you have 1 node. Fantastic. For your third molecular orbital, you need 2 nodes, all right? Remember, draw it as symmetrically as possible. So we can do this where 2, 2, 2. All right, that's pretty symmetrical. All right, for 3 nodes, what you can do is something like this. All right, that looks pretty symmetrical. All right, so you have 3 places where you're going to introduce discontinuity. All right, then for 4, what you can do is 1, 2, 3, 4. All right, that's a good symmetrical way to do this. And then for 5, it's just going to be 1, 2, 3, 4, 5. So there's going to be a change in phase between all of this. Now what we can do is going to be easy. We can just go ahead and draw these appropriately with positive and negatives to demonstrate changes in phase. So if we do positive, positive, oh, look, we've passed we passed something where there should be a node here. So we have to change phases. Again, there needs to be a node here. So once again, we change phases. All right, and then you do the same for the bottom, but opposite. All right, very easy. All right, and then same for each one, and you continue the same thing, and so on and so forth. All right, so try to finish this up on your own. The answer's in the textbook. All right, but this is very good practice. All right, follow these steps, and it will help you be able to draw the conjugated molecular orbitals for any conjugated system. Now, the last thing we want to cover before the end of this session, all right, is electrophilic addition. All right, when butadiene, like this molecule's butadiene, is treated with HBr, for example, all right, a similar process takes place as we've seen with any addition of any halide, all right, where your double bond is going to take the hydrogen, all right, and then this bond between them, we dump the electrons on the bromine, all right. This hydrohalogenation, all right, is occurring via mark addition, all right. So your hydrogen should be added here, and then your bromine should be added here. That's how we learned hydrohalogenation to go about, all right? But the thing is, when that hydrogen is added to this side, and for a moment you have this carbocation right here before your bromine comes and attacks and places itself right there to form the 1,2 adduct, what can potentially happen is some resonance where your double bond moves over here, all right, and now you have that positive charge here where the bromine can also come and attach itself, and what you form is this 1,4 adduct. So when a conjugated diene like butadiene is treated through hydrohalogenation, all right, you can actually get 2 products. 2 products are observed. And the formation of these 2 products, like we just saw, can be explained with this 2-step mechanism where you do your protonation to form a carbocation, all right, but this protonation can be create a more stable resonance stabilized form that happens and results in these two products being formed. Now, when the reaction is performed at low temperature, the 1,2 adduct is favored. At high temperatures, the 1,4 adduct is favored. So let's quickly just do 1 or 2 practice problems on this to really capture what happens, all right? So for A, all right, we're going to go ahead and do the hydrohalogenation for this conjugated diene. All right, what happens? Let me try to draw this better so that everybody understands. Let me make my double bonds a little prettier. Here's a double bond, and here's another double bond, right? We have our HBr. All right, this is pretty symmetrical, so we can work with any double bond we want here. All right, let's pretend this double bond takes this hydrogen. All right, fantastic. So what we're going to have here is a positive charge right there, because the hydrogen's going to add itself via mark addition. All right, fantastic. And then we have a positive charge here. Now you may assume, right, obviously, that the bromine's just going to go ahead and attach itself where that positive charge is. And what you would get is the following product. All right, this is our 1,2 adduct. All right, but what actually happens is some sort of resonance can also occur at the same time. All right, where we move our double bond over here. All right, and our positive charge moves over here. And what can happen here is now the bromine can attach itself in this position as well. And what you have is a 1,4 adduct. Now, how can we tell which one is the major and which one is the minor product? Easy. We look at temperature. This is at elevated temperatures. So our 1,4 adduct is our preferred product. All right, let's do one more. B. All right, again, symmetrical, so we can work with any double bond we want. All right, we have HCl. So let's go ahead and take this double bond. All right, it takes the hydrogen, and this chlorine breaks off. What we get is something that looks like this, where the hydrogen will attach itself right there, and so we have a positive charge right here. Okay? Now, from this product, from this, we can get an end product that looks like so. All right, which is our oh, sorry, it's not bromine, it's chlorine. Let me fix that very quickly. Chlorine, my bad. Oops, look at me, I'm all over the place. Chlorine. Right there. All right, that's our 1,2 adduct. Fantastic. Now this can still go through some resonance, right? We can move our double bond right here. And what we'll get, and I'll draw it in purple. We'll try to fit it in here. All right, what we get if we form our double bond here is the positive charge is now there. And bromine can attach itself, right? I mean, chlorine, I'm so sorry, can attach itself there as well. And you get your 1,4 adduct. All right, now, how can we tell which one is our major product? Easy. We have to refer back to our temperature, the temperature that this reaction is being carried out in. All right, and that's a low temperature. At low temperatures, our 1,2 adduct is our major product. I'll leave C for you to do. All right, I hope this session was helpful. Next time, we're going to go ahead and finish the latter half of chapter 16 where we talk about pericyclic reactions. All right, for the time being, good luck. Happy studying. Let me know if you have any questions, and have a great day.